Hey, it's me, Steve. It is May 23rd, still 2017. Time is 16:51, and temperature is 67 degrees Fahrenheit. This is a Geo-Rant. I am going to talk today about kind of chemistry and physics. Don't worry, no equations, because there was something in college that I learned that kind of stuck with me, and I wanted to address that here. Now, I'm a geologist, but geology isn't just looking at rocks going ooh ah. There's other disciplines within geology and other closely related disciplines like geophysics, which I took, geochemistry, which I did not take because me and chemistry did not get along very well. Geochemistry and paleontology were the only, I believe, the only geology courses at Illinois State that I never took. I took the rest of them, just not those two. Anyway, sorry about that, railroad tracks. But what intrigued me is liquids, okay? Now, most, oh, by the way, chemicals, I'll be talking about chemicals here, which I'm defining the scientific way. Basically, if something's made of atoms, it's made of chemicals. I'm not talking about how it's been hijacked the past 20 years to somehow mean toxin. But anyway, but I'm going to talk about the three main phases of matter that we're all familiar with: solid, liquid, and gas. There's plasma, but I'm not going to address that here. It's interesting that things don't like to exist as liquids. Materials like to be either solids or gases. Now, I'm going to show you a chart here with the temperature ranges, the melting / freezing point of some chemicals and their boiling points, and in between those, the temperature is the temperature range which they exist as liquids. And you're going to see just how narrow these ranges are. And this chart is based off 1 atmosphere of pressure here on Earth. Okay, if you increase pressure, you can actually keep things as liquids or solids longer. But I'm going to show you the chart, then I'm going to hit the highlights here. I'm going to show you the whole thing. There we go. There it is, zoomed out. Okay. Now, here on Earth, I'm not going to read all these to you. You can go back and look at them if you want. You see that common things like ethanol, carbon dioxide, iodine, or iodine, nitrogen. Those things have liquid phases that are, it likes to be a liquid for an extended temperature range, but it's still only a couple dozen to a few hundred degrees Celsius. This entire chart's in Celsius, by the way. I did include mercury on here just because on Earth here, at room temperature and pressure, it exists as a liquid. But freshwater and seawater are slightly different. See, when you start to add impurities to things, you can change, even at standard temperature and pressure, you can change their melting and their boiling points. Now, I included some metals on here too: lead, iron, copper. And those will have huge liquid. Those will stay liquid in the order of, 1,300 to about 1,500 degrees Celsius. They'll within a range like that. Metals will stay liquid in a higher temperature range than most other simple compounds will. I also put chocolate on here to illustrate a point. Chocolate doesn't really have a boiling point. It burns, and I'll get into that in a second. But it does melt at around the temperature of a human mouth, slightly under, a degree or 2 Celsius less. But chocolate burns. It doesn't boil. Why? Because it's very complex. It's not just like, hydrogen is just H2, carbon dioxide is CO2. In chocolate, you've got things like sugars. So you got glucoses, you've got fats, you've got all kinds of stuff in chocolate. And same thing with the wood. Wood will burn. It won't boil away. And I did have quartz on here because, quartz and glass are basically the same thing. But apparently, there's different types of glasses. So the melting point and the boiling point is a huge variance. But quartz will melt at about 1670 degrees Celsius, and it'll boil at about 2230 Celsius. So it's about 560 degree temperature range will exist as a liquid. So on here I went and I included some other things and their temperatures, and then I'll talk about like the surface of the sun, and these are all in Celsius, is about 5,500 degrees Celsius. The center of the sun is 15 million, okay? That's still not the hottest thing in the universe. The hottest natural thing in the universe, not our particle accelerators, just naturally occurring, are supernova. Those can be 100 billion degrees Celsius or Kelvin. When you're working with 100 billion degrees, that doesn't really matter much. The surface of Venus is 462. That's enough to melt lead. Okay. Interstellar space, on the other hand, is very cold. It's minus 270 degrees, about minus 270 degrees Celsius, or about 2.7 degrees Kelvin. Well, what's degrees Kelvin? Basically, degrees Kelvin, all that is degrees Celsius from absolute zero. So I think the addition, so whatever you have in Celsius, you add, I believe it's 273 degrees to it. Absolute zero is as cold as anything can get. You cannot get colder than that. Okay, there is no such thing as negative temperature. All right. So interstellar space is pretty cold. Now, the lithosphere, which is right below the crust in the mantle on Earth, it's about 500 degrees Celsius, but it's a solid. And even near the core mantle boundary, the mantle is about 4,000 degrees Celsius, but it's still a solid because you've got the pressure. The pressure is starting to, pressure can keep things, solids or liquids, longer. But or even like the pressure at the center of the sun is immense. It's huge, but it's all gas. That's because of the extreme temperature. But anyway, the outer core is about 4,400 to 5,400, and the inner core is about 5,400 to 6,100 degrees Celsius, which is hotter than the surface of the sun. But the solid core, even though that's well above the melting point for iron, or the boiling point for iron, it's under so much pressure, it's a solid. So you can keep things in certain phases, liquid, solid, or gas, if you apply enough pressure to it. But I'm going to talk about water now and ice, okay? Because, fresh water will freeze at 0 degrees Celsius, boil at 100, okay? But there's something interesting about water, all right? When it freezes, it actually expands, because it forms hexagonal crystals. But you can have warm ice. The conditions are not present on Earth to have it, but I believe it is ice. It's ice 4. If you can put enough pressure on water, about 2 gigapascals, or about 20,000 atmospheres of pressure, so 20,000 times the atmospheric pressure around you at sea level, which would be about 20 kilometers in depth. Like if you had a beaker of water that was 20 kilometers long, the bottom would start to form, that pressure would start to form ice. That's still twice as deep as the deepest trench on Earth. So we don't have any of this ice 4. But the crystal structure changes too. It's warm ice, even at room temperature, it'll become a solid. Ice 4 is still hexagonal. It's that other crystal system people have broken out of it, that trigonal, hexagonal crystal, so it'll form rhombohedral crystals. And the difference between a trigonal and a standard hexagonal crystals. A trigonal has one threefold axis of rotation, as where a standard hexagonal crystal has one sixfold axis. Other than that, I don't really see what the difference is. Who cares if it's 3 or 6? It's still six-sided. But anyway, so even water under immense pressure will solidify. And when you look out into the universe around you, you see mostly gases or solids. There's not really much liquid. And if you take a cup of water and were to expose it to the vacuum of space, it's not going to freeze. You know, even if in interstellar space where it's 2.7 degrees Kelvin, it's going to evaporate because there's no air pressure. It's just going to turn into a gas. And things do this all the time. It's why we can smell things. Even though something's a solid, it's still turning into a gas. Otherwise, you wouldn't be able to smell it. And you know, you can go from solid to gas. You don't have to have that intermediary of a liquid. But you look at, I mean, there are liquids out there. Don't get me wrong. I'm not saying there's no liquids outside of Earth. I am not claiming that. So I don't want to see those comments, okay? I'm just saying that in general, things do not like to be in a liquid state. You know, I mean, you look at the planets, they're all pretty much solid. We got some moons of Jupiter that might have liquid water under, or probably even that ice core. You know, I mean, liquids are out there, don't get me wrong. But you look at nebulas, they're gas. You look at the sun, it's a gas. The planets, solids, are gas. Jupiter, I know the inside of Jupiter is special due to the pressure and the composition. I know that. But it's just kind of odd, you know, things don't like to exist as liquids. It was just a thought I had. But anyway, I hope you learned something.